with 14 years experience in the platinum mining industry in South Africa. She's currently with Sibanye-Stillwater and is the competent person for the South African PGM resource business of the company. She holds degrees from the University of Pretoria and a master's degree from the University of the Witwatersrand. And she's been involved in studies at the Wits Business School and the university, a post-master's degree. She is actively involved in the GSSA Bushveld branch and currently holds the treasurer position. So she has the money. Nicole, with that, take it away, and we'll see what you have to say. Thank you very much for presenting today.
Great, thank you, Craig. Hi, everyone. So my talk is going to be slightly less scientific than the rest of the talks, and I think the message I'd like to give across is more sort of a practical one, I would say, how we extract the maximum amount, the economic value that we can out of the Merensky Reef, knowing how variable it is across the Western Bushveld.
Nicole, can I interrupt just for a second? Apparently,
yeah.
we're not seeing the right screen. We're seeing the we're not in presentation mode.
Oh, sorry. Better?
Try swap. Yeah, perfect.
There we go.
Great, thanks. So just as some way of introduction, after the integration of Lonmin into the Sibanye-Stillwater group, we now pretty much have 60 kilometers of strike area that we mine. And as you would imagine, this gives us some exciting opportunities, particularly as geologists, because it opens up a whole host of research opportunities that we can do across the lease area. So my focus today is going to be on the Rustenburg and Marikana operations. Just to sort of put into context, we have the 60 kilometer strike on the Western Bushveld. We also have some project areas on the Eastern Bushveld. And we are currently the biggest primary producer of platinum and rhodium, and second palladium producer, second to Norilsk. Our reserve base only on the SA PGM is 70 million ounces in reserve, and we have about 490 million ounces of resources. So as you can see, it's a huge real estate that we have. So focusing in on the Western Limb operations, we have the Rustenburg operations over here, now newly incorporated Marikana operations. And what I'd like you to have a look at on this plan over here is the red area is basically the mined out Merensky Reef. So as you'll see on the Rustenburg operations, much of the shallow, or pretty much all of the shallow Merensky has been mined out. We're now focused on the deeper areas. And at Marikana, we've only mined the Merensky on the western side of the property, with a huge amount of resource still available on the eastern side that is available. Just to put into some context in terms of Merensky production across the operations, annually we produce about 4.3 million tons of Merensky Reef, so that's a sizable amount. So looking at the facies variations, and why this is important is that the Merensky Reef, as we know, is variable. And it's variable in both the assemblages of the rock types as well as the distribution of where the PGE mineralization is sitting. And it's critical in the understanding of the nature and these variations in order for us to then economically extract the Merensky Reef and get the best value out of it. So starting on the Marikana, the Rustenburg operations, we have the typical thin pigmentoidal reef. As we move across to Marikana, we see an area of large variation, transition, where we see multiple facies, mixtures between a pigmentoidal and a non-pigmentoidal facies type. And as we move to the far eastern side of the Marikana operations, we move into a thicker, up to 15-meter pyroxenite reef. Obviously, not all of it is well mineralized. We see a very small portion that would be payable in that regard. So if I zoom in to the Rustenburg operations, as I mentioned, a lot of the shallower Merensky Reef has been mined out, and we're currently focusing on the deeper areas. And the reef facies, and as Gordon mentioned previously, you know, this is not new work, and these plans are dynamic. So as we're mining, we're getting new information, we're updating these plans continuously, underground mapping, the observations on the ground. So just typically, as a very basic summary, we're moving from west to east. We have a rolling reef component here. The typical thin reef spans most of the area. We do pick up some what is termed thick reef portions, and then we have the contact reef. And these reef facies types are essentially characterized by the different reef lithologies, the different footwall lithologies, the differences in the reef elevation within the stratigraphic succession, and the width and position of the mineralization in the package. So if we look at the rolling reef, what that typically is, it's a reef of about 30 to 40 centimeters in thickness, displaying shallow potholing of the reef. And due to this, we do see that the bottom contact is poorly developed. Moving across to the thick reef that is picked up, here the reef can be up to 90 centimeters in thickness, and it has a top bounding chromatite layer and two interstitial chromatites within the reef. The thin reef, which is the most typical facies that's encountered, is about 10 to 20 centimeters thick and has two very well developed chromatite layers that bound the reef. The smaller component of the contact reef is essentially a single chromatite layer of about 3 centimeters thick, with your hanging wall and your footwall units as normal. So just to zoom in on an image of a typical Merensky Reef section at the Rustenburg operations, we have your typical pegmatodal peroxenite reef, bounded by your top and your bottom chromatite, which in most cases is well developed. And the thickness of this reef is quite regular, between 5 and 60 centimeters. We do see some local variations, example where we have the contact reef and the thick reef, but typically it's pretty standard. And the assemblage has a peroxenite hanging wall of up to 1.2 meters. As William was alluding to now, we have about a 5 to 10 centimeter northosite footwall, the immediate footwall to the reef, which grades then into the norites. So moving across to the Marikana operations, things get a little more complicated here. We're moving out of that pegmatoidal facies now, and we're picking up the predominantly peroxenite facies. At the K3 shaft, we do see quite a mixed bag there, and we do get a lot of different facies at the shaft, which makes mining that quite challenging. We see the same at our 4-belt shaft, and I'll go into more detail using that particular shaft as an example. As I mentioned, we've only really mined on the western side of the property, and that's just because this thicker peroxenite facies is a lot more difficult from a grade control perspective. The grades are lower, and it thickens up to 15 meters. And in that sense, choosing where to put your resource cut becomes a challenge. So just to take you through the facies at Marikana, we go from this thin pegmatoidal facies, which is pretty much the same as what we see at the Rustenburg operations, about 1 meter in thickness, and we're moving across to the east where we get up to 12 meters of the Merensky peroxenite. And what's critical in the understanding at Marikana of these facies are these lateral transitions. It's important, particularly for grade estimation. We use these facies domains as hard boundaries. So using, as I mentioned, we look at the lithological assemblages, and what's critical at Marikana is the occurrence or absence of chromatite layers. That's one of the biggest criteria we use for facies determination, and it's also driven largely by the value distribution, or where the mineralization sits. And as I mentioned, we do get a variable thickness of the Merensky peroxenite across the property. Just to show some images of the typical facies that we get. Here what we would term this sort of a thin peroxenite facies. The lower chromatite is the only one that is developed onto the footwall and orthosite, and then we just get the variable thickness of the peroxenite. Another peroxenite facies where we have an upper and a lower chromatite developed. This particular example over here where we see the pigmentoidal peroxenite, that's to the western side of the property, and this is pretty similar to what we see at the Rustenburg operations. Again, just another image where we see the undulating footwall here of the lower chromatite of the peroxenite facies. So if we look at the grade distribution, this is just an image of the regional grade distribution from Impala Mine across to Westerns in the Brit side. Just important to note, the grade is typically concentrated around the chromatite layers, which is well known, as well as some concentration in the pigmentoidal peroxenite reefs. And important to note, as we move from west to east, as the peroxenite thickens up, and we actually, there should probably be another image here because we basically lose these chromatite layers. They're not developed at all, and we then lose the marker. The lower chromatite is developed, but this upper one disappears. Although we do still see the mineralization, the marker horizon does disappear. So if we zoom into the grade distribution at Rustenburg, these are the four typical reef types that we see. We have the contact reef where it's just basically that chromatite layer. We have some mineralization into the hanging wall and the footwall units. And the three pigmentoidal facies where we see the concentration of the grade essentially around the chromatite layers within the pigmentoidal reef in all these cases, and some mineralization going into your hanging wall and your footwall. And this becomes important when we look at the resource cuts, because as you see, these are very thin reef types. In terms of the determination of the resource cuts, at the Rustenburg operations, due to the thinner reef, we have to take a mining envelope that includes varying amounts of the reef, the hanging wall, as well as the footwall components. So how this is done, again, like I said, this is nothing new. This is used industry-wide. Histograms are used industry-wide because it gives us the best understanding of where the grade is sitting and how we can best extract the grade at practical mining widths. So typically, we generate histograms at 10 centimeter intervals because that's typically what the sampling intervals are taken at. And looking at this, just a quick glance, you can say, well, I mean, your best grade is going to be over this interval. We would then call that our best cut scenario or parameter, giving us our highest average grade. However, the issue we have with this from a practical perspective is this is only over 70 centimeters. It's not practical to mine that. It's because of the mining method, the rock engineering constraints, there's various other issues that we have with that. We have to then open up the cut to say what is safe to extract and what is practically mineable, taking into consideration all the constraints that we face underground. So the final cut that the resource cut is decided on a number of these factors. And in this particular case, we settle on a 1 meter, 5 centimeter cut with some material taken from the hanging wall, the bulk of it taken from the footwall, because that you see there is some grade distribution down into the footwall. And this varies across the different facies. And obviously the implications here is that anytime you introduce waste into the system, you have issues with recoveries and those types of things. So, it's important to also bear that in mind. As we move to Marikana, the grade distribution becomes a little bit more complicated. Over here we have our pigmentoidal facies, and here we have the non-pigmentoidal facies where it completely disappears. And these are the typical grade profiles that we see. And as you see, it changes from the west to the east, where we have a more what we would term bottom loaded on these chromatite layers and in the pigmentoidal pyroxenite, moving across to the thicker pyroxenite, where, as I mentioned, we lose this marker here, this chromatite layer. We still retain this, but to practically mine 15 meters is not going to help unless you're open casting it. So it becomes a lot more difficult to choose where you place your cuts, where you don't have marker layers developed. So as I mentioned, we see the peaks on the chromatite layer, and that's why it's critical in understanding when we define these facies, the absence or whether the chromatite layers are developed or not. I think, as you can see there's limited, pretty much no grade up into the hanging wall, very limited on the contact here in this particular case, this facies. We do see some grade mineralization going down into the footwall. Again, on the pyroxenite facies, very little though. It's more so where we have the pigmentoidal reef developed. And again, we have a look at it, you have your best cut parameter, but the question you have to ask yourself, is that practically mineable? And I suppose a good thing about the facies types at Marikana is that because we have this thicker reef, we don't necessarily have to take as much of the diluting hanging wall and footwall material, which from a recovery perspective makes it a little bit easier. So again, the process of selecting the mineral resource cuts, it's similar to Rustenburg using the histogram. And as I mentioned, the mineralized portion is thick enough that we can have limited amounts of hanging wall and footwall material. So when we move from a resource to a reserve conversion, we do see limited waste coming into the system. So again, we're generating histograms on 10 centimeter intervals. And the key difference here is that when we build the histograms at Marikana, we use key layers to hang our resource cuts. So for example, over here, we see 2 chromatite layers developed. We see a variable thickness between the 2 chromatite layers with varying grade. And this particular histogram is built on the upper chromatite layer. And typically, when we decide on the cut, we would take this as our starting point and work, what is practically mineable, looking the thickness that we can mine. Also, what's important to note here is looking at a fixed versus a variable cut. So typically on the Merensky, it's more practical to have a fixed cut because then you typically have a constant thickness. You have typically a constant grade per facies type, and it takes a lot of the guesswork out of it. Where we see variability and where we introduce variable cuts is where we have these chromatite layers, and the thickness between the 2 does vary. So when we choose resource cuts for these particular examples, we do look at a variable cut, which does complicate things a little bit, but typically that gives us the best grade over that interval. In this example here, we've put the histogram on the lower chromatite, and we just look at this we would typically call a bottom-loaded mineralization, where this is the lower chromatite sitting on the footwall. So we have some grade going down into the footwall there, and typically the cut would look something like this on the red arrow. And again, like I mentioned, we always have to have in the back of our mind is ideally as resource geologists, we would like the best grade to be extracted. However, from a practical perspective, they can't mine these thin envelopes. So just taking you to some of the variability that we see at Marikana. In some cases, we have local variation, and we see transition zones between facies, and we understand those. We've studied them in depth. As I mentioned, there are dynamic plans, so we're continuously improving on those. However, in some areas, we cannot physically domain them out as facies zones. They're too random the data is distributed too far apart. We cannot physically have these different areas. This obviously makes it difficult to estimate the grade. You have a risk of over or underestimation in these mixed zones, and obviously it's not ideal when you're building mine plans to have too much variability. On the Rustenburg ops, we do see some variability in the facies. It's pretty well understood that the work has happened over a long time, but typically we see that these are more sort of on a localized occurrence. The resource cuts are very similar, incorporate varying amounts of the hanging wall and the footwall, so you have a lower risk if you're mining one facies type and you encounter another one. Typically the cut would be similar. You wouldn't have to alter your stope too much, and you could still extract what needs to be extracted. The issue that we have at Marikana, we have two main zones of mixed facies. At our K3 shaft, and I give the example here on the right, we have an example where we move from a thin pegmatoidal facies, as we see at the Rustenburg ops. We lose the pegmatoidal pyroxenite, and we move into what we call a thin facies locally at Marikana. And thankfully, in this case, with the grade being concentrated around the chromatite layers, if you're mining this cut over here and you lose the pegmatoidal pyroxenite, you have little risk that you're going to leave grade behind when you lose it and you move into a scenario where you have a thinner facies like that. They're both bottom-loaded facies, so typically, it wouldn't be too difficult to extract that. If we move to our 4-belt shaft, and here's just an example or where the shaft is. We have two facies that we have identified, and here we have an illustration of the two. So we have typically, and in the greatest proportion of about 90%, we have what we locally call the West Platts facies. This is a thick pyroxenite facies where we see an upper chromatite developed, a lower chromatite developed onto the anorthosite footwall, and the thickness of this pyroxenite is variable. Typically, it can be up to 2 meters thick. So when we mine this, typically we would mine from this upper marker here, and we would go down a certain thickness to extract the maximum grade, and that's how they would typically mine that. As you see now, when we transition across, you may be happily mining the West Platts facies, and you get a case where this upper marker now disappears. Your pyroxenite thins to about 50 centimeters. That's typically what we see in the thin facies. And now what do? You have to alter your stope. Unfortunately, you've already developed, you can't necessarily cut your stope to 50 centimeters. It's not practical, which typically means we have to mine through this facies at the similar parameters to the West Platts facies. And as you would imagine, that then dilutes the grade. So how do we go about predicting how much of this dilution we're going to introduce? It's a low-grade facies. It's moving from a more top-loaded to a bottom-loaded grade distribution. And how do we handle this from a mining perspective? So in order to accurately estimate the grade that we're going to extract in the mine plan, we had to look at a different approach to how we mine. And if we look at this plan here, sorry, it's a little bit small. I don't know if you can see the blue points essentially are where we intersect the thin facies, and the red is basically the West Platts. So as I mentioned, we're sitting with about a 90% West Platts, 10% thin, which we understand from the data as well as underground mapping, stope observations that are done daily. So I think we have a fairly good understanding of the proportion of the two different facies, and that's a good starting point for us to look and see how do we estimate the grade at this particular shaft. So what we did then is we looked at a probabilistic approach in order to estimate the grade as accurately as we possibly could between these two facies. So what we did was we gathered all the underground sampling, the surface sampling that we had available, as well as any mapping that was used, that was done underground, which is typically in all our raised development. as well as the slope observation points. And those are key, because you see the amount of data that gets added purely just by using those slope observation points. And what those are is just, our evaluation. People are going on the ground, observing the slopes, they're documenting what they're seeing, and that is captured, and we can then extract that information and see where the facies are lying. So you'll see again, the blue is the occurrence of the thin facies, and the red is the occurrence of the Westplatz facies. Data validation is also key to this process, because obviously there's a lot of noise that comes through. We have to discard a huge amount of the data. And when I mentioned the transition from the Westplatz to the thin facies, that also complicates things, because as we move from the Westplatz across, we typically lose that upper chromatite layer. But for a small portion in that transition, the peroxenite retains its thickness. So from an observation point of view, they may observe that as thin facies, but it's not pure thin facies. It's what we would call more of a transitional, where it's not Westplatz, it's not thin, it's somewhere in between. So we have to be careful not to include that data, because that obviously sprags things a little bit. So what we did then is basically everything where thin facies is found, we give an arbitrary 1 number, everything else is a 0, and we go then about modeling the probability of encountering thin facies. So what we did then is we took all those points and we built an inverse distance model. And what that did was basically, you'll see the blocks here, it gives us then a percentage or a probability of encountering that thin facies per estimation block. And what that then does is we can then accurately per block proportion the thin to the Westplatz facies and get a better average grade per block than just saying everything is Westplatz and this is the grade you're going to achieve there. Something that's important to note as well is obviously going back to this slide here, where we have the data, the confidence in those probabilistic proportions are a lot higher. As you move into these areas where we don't have data, it obviously becomes, it's anybody's guess, it's the best guess we have at the time. So it's important that the probabilistic focus is more on what we would term our budget or our short-term areas where they're currently mining. And in this way, we get a better grade estimate. We can then predict and say, you're getting a 10% diluting factor in this budget plan, and we can plan for it, and it then essentially dilutes the grade accordingly, and we get a better estimate and what we can work towards in terms of the grade at the shaft. So I think in closing, a critical consideration of when we build these mineral resource estimates is the selection of the resource cut. A lot of work goes into that, and it's influenced by not only the grade distribution. We have to look at the mining method, the rock engineering constraints, how to practically mine it. And where the mineralization is variable, we need to understand the lithological thicknesses, the concentration profiles. It's critical that we constantly updating the lateral transitions between these facies, because they are so key in building the grade models. As I mentioned, the resource cut, we may have a fixed thickness cut, which is the preferable cut. In some cases, we do unfortunately have to apply a variable thickness cut. And in some cases, we need to make allowance, particularly on the Rustenburg side, for diluting material to accommodate practical mining and have safe extraction at the end of the day. And as I mentioned in the example, we do have conditions that arise where we have this mixed facies. We can't domain them out. They coexist over short distances, and we have to use proportions here to and the use of the probability approach to better get an estimate of the grade. Thank you.
Thanks very much, Nicole. Well illustrated talk, well presented. Thank you very much. We'll take a couple of questions. George, you have a question?
Thank you, Craig. Thank you, Nicole. That was a very good talk. I'm just curious as to the fact that you haven't once mentioned the infamous word kriging in your resource estimation. I know about stuff like resource estimations in the bushveld mines, and some people have consistently used kriging as part of their resource calculations. And you've gone and just gave us a very good talk about using a different and in fact an older method, probabilistic and inverse distance models. Now, have you actually tried the kriging story before you came back to the inverse distance model?
Yes, George. So in terms of the bulk of or most all of the resource estimation is done using ordinary kriging, and for this particular area that I was talking about, it was always done with ordinary kriging. Unfortunately, as I mentioned, the issue with that is because we couldn't domain the thin facies out particularly, that shaft area or that particular facies zone would only be used. We would only use the West Platts grade, which, as I mentioned, we then run the risk of overestimating the grade, and we do see that, you know, versus when we do recon between the actuals versus the budget numbers. You know, obviously we're constantly doing a recon to make sure that those numbers don't drift too far apart. So ordinary kriging is what we use. Normally we had to just, in this particular case, follow a different approach.
Thank you.
Wolfgang, you've raised your hand.
Yes. Hello. Yes. Yeah. Just a quick question. I was wondering for a long time, actually, and there are a lot of mining people here in this group. They might be able to answer this. Are there any areas, places in the Merensky Reef, Western Bushveld, Eastern Bushveld, where the grade is actually zero or very, very low, say on a decimeter to meter scale? Does that occur at all?
Yeah, I don't know, maybe someone else can answer that. As you saw from the grade profile, I would imagine the only place that we get that is in the thicker peroxenite facies to the east of the property. You know, we could look at the grade profiles over there and see where the grade disappears. I don't know if that answers your question.
Graham, you have your hand up.
Hi, yes. I was just curious, you spoke a bit about the data validation and obviously the importance of that in what you're actually modeling. I was curious about how you're actually deciding what is noise and what is true, especially when you have a situation where a lot of the facies look one way but actually turn out to be another.
So typically, Graham, when I talk about noise, a lot of it is you know, the actual facies that get assigned to the stope observations. So what I did was, you know, they pick up a whole lot of other stuff, you know, pigmentoidal facies. Obviously, these are localized occurrences. So, you know, all of that is removed. So I clean the data set as much as possible to get purely the thin facies. And how I do that as well is I look at histograms of the actual channel thickness that they pick up. So when that transitional facies I was talking about, as I said, the peroxenite retains its thickness. We just lose that upper chromatite. So I see if it's logged as a thin facies, but it's 1.5 meters thick, I know, you know, that's not your typical thin facies. We're sitting in a transition zone. So there's a lot of statistics that go into it, looking at histograms, comparisons, plotting things spatially. So a large amount of work goes into that data validation.
Okay, thank you.
Okay, I'm going to take two more. Gordon, a quick one.
Yeah, look, there would be the issue of dead areas. There certainly are dead areas, and they were borne out in particular at Attock in now called Bacone, where we would get what we called a washout, where the sulfides and more importantly the PGEs seem to dissipate into the footwall and dribble down through the footwall into a lower horizon and might accumulate at some elevation lower down, leaving behind the texture and composition of the pegmatoidal peroxenite that previously hosted those sulfides. So certainly they do occur, and they occurred at Rustenburg as well. I can't speak for the areas to the east of Rustenburg. We really didn't have access to much data from that. Then I saw there was a question around quartz coming in. The Merensky Reef does contain a small amount of quartz, as do many of the other PGE-bearing reefs around the world, and notably outside Sudbury, a project called River Valley, it's now under NAM, where we had blue quartz. And that was an indicator where things were changing in the system.
Thomas?
Nicole, thank you for the nice presentation. I just wanted to know, what's your sampling interval underground for picking all these grades?
Thomas, it's quite tight. We're sitting on about 10 to 15 meters on dip on the Merensky and on the Marikana operations. It opens up at Rustenburg. I think they're sitting on about a 60 by 60 meter grid. But because we have this huge variation in facies, we have to keep a tight control on the facies variations and the domains. So we have a very tight spacing. Particularly at Full Belt, why I mentioned that the data is a bit sparser, we do have a different mining method. So we're moving from the classic up dip, down dip to a breast mining. So we see large differences on strike.
My sound is gone.
Sorry, we've got some interference here.
So the difference there is, you know, we have a lot of dip samples, not necessarily enough strike samples, and that's what makes sort of domaining difficult.
Okay, I'm going to take one last question from Wolfgang. There's some stuff going on in the chat box. Have a look at that. Wolfgang, last question.
Yes, a quick one again. How common are massive sulfide pods in the Merensky Reef, and how big can they be? And is there any grade in those?
We do see a lot of sulfides, particularly in the pegmatoidal pyroxenite reefs, more so than in the pyroxenite reefs. They're large grain, but not, I wouldn't say that they're huge or massive or clustered. I mean, it's about, I don't know what you would compare it to, but we do see big sulfides, like I said, particularly in the pegmatoidal pyroxenite reefs.
Okay, I'm going to halt the discussion there for our next 15-minute break. I guess if we come back at somewhere around 12:25 or 12:20 to 12:25, we're a little bit behind, but I think the discussion has been good and we've tended to let it run. Nicole, thank you for a very good talk. Thank you to the other speakers of the session. Stay online. Let's have a 15-minute break.
While everyone has a tea break, and I come in on a random point here, which ties in with Nicole's thing.
Sure, go ahead, Gordon.
I've long held the opinion that the Merensky Reef is a misnomer. It's by no means a reef. It is a value zone. It starts above the top